Lesson 1.5 is going to introduce us a bit to domain and range. The domain is the set of all input values. Those are also the x values, or the values of the independent variable. The range, on the other hand, is the set of all output values, or y values. Those are also the dependent variable. Remember, the independent variable causes change in the dependent variable. The domain and the range can be expressed in more than one way. So when we're given a finite number of values in the domain and range, what we're going to use is something called roster form, which is just a comma-separated list. If you're not sure what finite means, it's essentially the opposite of infinite. There are like a countable number of items in the set. So, what do we do when we approach a traffic light? What we do when we approach a traffic light is a function of its color. So if we're trying to figure out the domain and range here, we need to know what are the input values and what are the output values. If you remember, the is a function of phrase helps us figure that out. Whatever is a function of something else, whatever it is a function of, this part here is always going to be your input. The color causes change in your behavior as you're approaching the light. So the colors of the traffic lights are going to be green, yellow, and red. Now, what is your behavior as you approach that light? When it is green, you're going to just continue to go through the light. When it's yellow, you're going to slow down, be cautious. Hopefully you won't speed up. And if it's red, you're going to stop. So there's our domain and range in roster form, which is just a fancy way of saying a comma-separated list. When we have an infinite number of values in the domain and range, we're going to use either something called set builder notation or something called interval notation. So, how do I know that there's an infinite number of values in this domain and the range? Well, if we look at a graph, right here, it's starting at this point here with an x value of -2. So it includes the x value of -2. Travel up here, we have an x value of -1. So -2 and -1 are included, but so are every single x value in between -2 and -1, which means there's an infinite number of items in that set. So for our domain, if we're looking at this graph, like we said, it starts here where x equals -2. So that's our beginning. Then we have to see if we can find our end. So we look to the right. And when we look to the right, we see that this line continues forever. That's what that arrow indicates. It's going up forever, but it's also going to the right forever. And that means that as it moves to the right, it's going to approach positive infinity. So our domain doesn't have an endpoint in that direction. So in set builder notation, we start with this brace, and then we write x with a vertical line. That vertical line just means such that, and then we write our inequality, bounded by the -2 on one side, your infinity on the other side, the x variable in the middle. Then you have to write your inequality symbols. So that -2 is the smallest value, so it is going to be less than x, and infinity is the greatest value, so x is less than infinity. -2 is part of the domain, so we have to include it. So it's less than or equal to. Now, infinity, you might think we are going to include it, but there's this rule: we never include infinity. It's not an actual number, really, so we don't include it. Now, interval notation, it's going to still include these key values here of -2 and positive infinity. And it's also going to indicate whether or not we include those values. It's just going to be indicated in a different way. We have a curved like parentheses from when we don't include something. And we have a square bracket for when we do include something. So we are including the -2, we are not including the infinity. Moving along to the range, our y values. And I see right here, we have a bottom. We have a bottom at -1. But just like with the x values, we're not going to have a maximum value. It's going to continue to go up towards positive infinity. So for our range, we're going to say y such that. Now here we're beginning with -1. It's included, so we have the or equal to, and then positive infinity. And again, for interval notation, we're going to include the -1 with a bracket and exclude the positive infinity with a parentheses. Lastly, we're going to look at what we might have to do when we're given the actual function rules. So sometimes we have to look for domain restrictions or values of x that can't exist in the domain. And there's two main scenarios where that can occur. When we have rational functions, because in rational functions we divide, and there's a specific value we can never divide by. We can't divide by 0. So we have to see if there's any values of x that would make any denominator equal to 0. If it was more complicated than this, we would set up an equation we would solve, but this one's pretty straightforward. If x was 0, we would have an undefined function here. So for the domain, we just have to say that x exists, all is good, as long as x is not equal to 0. The other type of function that can often have a domain restriction is a radical function, something that has a square root like that, because we cannot have a negative under the radical. Now that's true for square roots, that's true for fourth roots, sixth roots, eighth roots, any even root. It's not true for cube roots, but here we're really just concerned about square roots. So we need to make sure that this is not negative. So how do we do that? We set up an inequality saying that it must be greater than or equal to 0. And then we just solve that inequality. And that is the expression that we can put in our set builder notation. So we start with x such that x is greater than or equal to -5. So as long as that is true, this equation won't be undefined. If you have any questions, let me know.